Hey, my name is David Taylor, and this is my third video on Fibonacci numbers, which I call Fibonacci Trains, and I think you'll find this kind of amusing. So let's proceed. Here's the outline. First, I'm going to state the problem, and then I'm going to derive a formula for the number of Fibonacci trains of a given length. I have to tell you what a Fibonacci train is first, but anyway, just to remind you, here's a table of the first 24 Fibonacci numbers. They grow pretty fast. By the time we're up to F24, it's already over 46,000. But the thing I want to point out to you right now is that the Fibonacci sequence starts with 2 ones. That's the only repeated number in the sequence. After that, they keep growing. So just keep that in mind for now. We'll use that fact later. Anyway, so here's the statement of our problem. So imagine you have a set of trains consisting of 2 types of boxcars, which we'll call short and long. So short boxcars are 10 meters long, and long boxcars are 20 meters long. And such train can consist of any combination of such boxcars in any order, but cannot have any boxcars of any other lengths. So that's what I'm calling a Fibonacci train, which will, for reasons will become clear as we proceed. And our problem is to determine the number of possible Fibonacci trains of a given length. So let's just start with a few simple examples here. So I'm just going to let capital N sub little n denote the number of possible Fibonacci trains of length 10n meters. And you'll note that every Fibonacci train has to have a length that's a multiple of 10 meters, since the boxcars are 10 and 20 meters long, respectively. And so those are multiples of 10 meters. The whole train has to be as well. So can we find a formula for capital N sub little n? That's our goal. That's my goal in this video. And I will do that by the end of the video. But before doing that, let's look at a few simple cases. So the simplest case is little n equals 1. So suppose we want to know how many Fibonacci trains there are of length 10 meters. That's capital N sub 1. Well, in this case, it's pretty obvious. A Fibonacci train of length 10 meters can only consist of one small boxcar. So capital N sub 1 is 1. That case isn't too exciting. What about length 20 meters? In that case, it turns out there's 2 possibilities. Either the train consists of a long car, which has length 20 meters, or 2 short cars, each with length 10 meters. So we have capital N sub 2 equals 2. Let's look at the next case, n equals 3. That would be Fibonacci trains of length 30 meters. How many of those are there? Well, let's look at all the possibilities. So we can either have 3 short cars, or we can have a long car and a short car. But there's 2 ways you can arrange a short car and a long car. Either you can have the long car in the rear and a short car in the front, or vice versa. Short car in the rear, long car in the front. So that's a total of 3 possibilities. So capital N sub 3 is 3. Now, I'd like to look at a couple more cases, but it becomes a little cumbersome to keep drawing trains for each case, even though they look really nice. So I'm gonna simplify my notation here. Instead of drawing a short box car, one of these red cars, I'm going to use the symbol S, and I'm going to use the symbol L for a long box car. That's the blue one. So I'm going to abbreviate these possibilities of Fibonacci trains. Let's look at them again. Here was the first case we considered. One short boxcar, that's just S. And then one, in the case n equals 2, we had 2 cases. One long boxcar, that's L, or 2 short boxcar, that's going to be SS. And in the case n equals 3, we have SSS, LS, and SL. And that's all I'm saying here. These are the possibilities. The only possibility for length 10 meters is S. For a length 20 meter Fibonacci train, there's 2 possibilities, L or SS. And for a train of length 30 meters, there's 3 possibilities, SSS, LS, or SL. As I did in my diagrams, we're going from the rear of the train to the front of the train. So the rear's on the left and the front's on the right, the way I've drawn these trains, because the trains are all moving to the right. So, and it's the same way with this shorthand notation. So, anyway, we already showed with our pictures I showed you earlier that and 1 was 1, and 2 was 2, and 3 is 3. So now I'm just repeating that here. I also like to derive formulas for n 4 and n 5. And you might think that n sub n is n for all n sub little n. Actually, that's not true. And you'll see that when you look at the next two cases. So now let's consider little n equals 4. And it's not hard to see that these aren't too hard to evaluate. So this would be a Fibonacci train of like 40 meters. And in this case, it turns out there's 5 possibilities, not 4. And the possibilities are all short trains, or you can have a long train and 2 short trains, and the long train can be in, or the long car can be in any of 3 possible positions. So you have LSS, SLS, and SSL. And finally, you have one other possibility, and that's LL, 2 long box cars. So that's a total of 5 possibilities, so n4 is 5. And finally, let's consider the case little n equals 5. In that case, it turns out there's 8 possibilities. Let's just go through them all. This is more complicated. If you kept doing this, they get more and more complicated. So I think it's a good idea to stop at little n equals 5. But in this case, it turns out there's 8 possibilities. You can now have 5 short box cars, or you can have 1 long and 3 short ones. The long can be in one of 4 positions, either rear, 2 positions in the middle, or front. And the other possibility is 2 long cars and a short car. And there's 3 possibilities for that, because the short car can be in any one of 3 positions. So you have 1 plus 4 plus 3, that's 8. So there's n5 is 8. Okay, and I don't know if you noticed a pattern here, but I'm going to illustrate it right here. You should have known something interesting, or maybe you did, about capital N sub little n. It turns out these numbers are 1, 2, 3, 5, 8. Those are Fibonacci numbers. But they don't start at the beginning of the sequence. Remember I told you that the Fibonacci sequence starts with 2 1s. So F1 and F2 are both equal to 1. So we really have to shift the Fibonacci sequence by 1 index. So this number here is really F2. This is F3, and this is F4, F5, and F6. So it looks like capital N sub little n is equal to capital F sub little n plus 1. At least that's true for little n going from 1 to 5. And just to beat that in the ground here, I tabulated capital N sub little n and capital F sub little n plus 1. And you'll notice that they're the same for all these 5 cases. So now what we'd like to do is we'd like to derive a formula. And it looks like we found a pattern, but just looking at a finite number of cases isn't going to be enough to prove this formula. This is the formula we're conjecturing right now, that capital N sub little n is capital F sub n plus 1 for every possible positive integer n. So how do we prove that? Well, we proceed as we did in my last 2 videos, using the method of mathematical induction. So this time, and this is a little more complicated this time, because in this case, we have to look at 2 base cases, not just 1. So we look at the base cases n equals 1 and n equals 2. And we already saw that formula 1 works for all little n up to 5. So that takes care of these 2 base cases. So now we can proceed to the proving the induction hypothesis. And this time, the induction hypothesis is actually going to involve 2 statements rather than 1. So our induction hypothesis is going to be that for a particular value of n, as well as its successor n plus 1, then we're assuming that equation 1, this equation here, holds for both of those cases. And then we want to prove that it also works for n plus 2. And it turns out that that is enough to prove the formula 1 for all n. So let's do that. And just to spell this out a little more explicitly, these are our assumptions, where n is now an arbitrary positive integer, and we're assuming equations 1 and 2 that capital N sub little n is is f sub n plus 1, and capital N sub little n plus 1 is f sub n plus 2. We already know those equations hold when n is 1 and 2 because we verified them. But now we want to prove formula 3, that if it holds for some n and some n plus 1, it also holds for n plus 2. So that will complete our proof if we can prove that. So this proof is a little messy, but I think you'll like it once you get it. So really what we want to prove, like I said, is formula 3 from formulas 1 and 2. And the trick here is to evaluate capital N sub little n plus 2 in terms of capital N sub little n and capital N sub little n plus 1. Because we already have formulas for these guys, so that'll give us a formula for this if we can find a relation. So to do this, let's consider first all Fibonacci trains of length 10 times n plus 2 meters, and that by definition is capital N sub little n plus 2, the total number. So clearly every Fibonacci train of that length has to consider, every chain of any length actually has to have either a short or a long boxcar at the rear. That's pretty obvious because those are the only two types of cars that are available. So let's consider each case in turn. So let's consider first the case in which the car at the rear is short. Then the remainder of the train, which we can think of as another Fibonacci train, has now length 10 times n plus 1 meters because we've subtracted 10 meters from 10 times n plus 2. And we can think of the remainder of the train as a Fibonacci train itself because it consists of short and long boxcars, the same short and long boxcars as the whole train. So, and we know there's capital N sub little n plus 1 such trains. So that means there's also capital N sub little n plus 1 Fibonacci trains of like 10 times n plus 2 meters with a short boxcar in the rear. But that's not all of them. We also have to consider the cases where the train in the rear is a long boxcar. So in that case, and it's the same kind of analysis, the remainder of the train now has length 10n meters. So, and we can think of that as a Fibonacci train itself. And we know the number of those trains is capital N sub little n. So that means that there's also capital N sub little n Fibonacci trains of length 10 times n plus 2 meters with a long boxcar at the rear. So now we've taken care of all possible cases. Either the Fibonacci train has a short boxcar at the rear, in which case there's capital N sub n plus 1 possibilities, or it has a long boxcar at the rear, in which case there's capital N sub little n possibilities. So we just derived this formula. The total number of total number of possible Fibonacci trains of like 10 times n plus 2 meters is equal to, and by definition that's capital N sub n plus 2, that's equal to capital N sub n plus 1 plus capital N sub n. So we just proved this formula. And I think you should notice something interesting about this formula. It actually turns out it's the recurrence equation. It's the same recurrence equation for the Fibonacci sequence. So that should already tell you that this the answer we expect should involve Fibonacci numbers. But let's continue. We're almost done. So now remember that we our first assumptions of the induction hypothesis were capital N sub n was f sub n plus 1 and capital N sub n plus 1 was f sub n plus 2. We just plug in those formulas into equation 4, which we proved, and that gives us this formula. So we have capital N sub n plus 2 is capital F sub n plus 2 plus capital F sub n plus 1. But now we're kind of in business because we already know the recurrence equation for the Fibonacci sequence, namely this equation. For every positive integer m or non-negative integer m, this equation holds. That's the recurrence formula for the Fibonacci numbers. So we can in particular we can substitute n plus 1 for m. That gives us this equation: fn plus 3 is fn plus 2 plus fn plus 1. Well, that's nice because notice we have fn plus 2 plus fn plus 1 up here. That means that the right side of this equation is really f sub n plus 3, but that is exactly what we were trying to prove. We just proved this. Capital N sub n plus 2 equals capital F sub n plus 3. And that actually completes our proof because we proved the induction hypothesis for every positive integer n. And that was all we had to do to complete our proof of equation 1, this equation, holding for all n, every positive integer. So we just proved that formula. And that completes the proof and gives us a formula for the number of Fibonacci trains of any given length. And just as an example, this may surprise you, but just suppose we wanted to know the number of Fibonacci trains of like 200 meters. It turns out that using that formula, that would be n sub 20. That's equal to f sub 21, which turns out to be 10,946. So that's the number of possible Fibonacci trains of like 200 meters. That's quite a few. These numbers go fast. But anyway, that's what we proved. And that concludes my video. And please, thank you for watching. And please subscribe to my YouTube channel, Dave's Math channel, if you haven't already. And I'll see you next time.